Thank you. Okay, thank you. So this talk kind of comes out of the following. So in the mid to late 1980s, a certain badass Russian mathematician named Viktor Kolyvagin made a valiant attempt to prove the Birch and Swinnerton Dyer Conjecture. And he proved it for curves with analytic rank 0 and 1, modulo some extra help from people like Bumfrey, Hofstein, Murdy, Gross-Zagier, and so on, and later on Wiles and so on. So the thing is, he only proved it for rank 0 and 1, but he certainly thought about the conjecture in general. And the point of this talk today is to just kind of look again at his sort of classical, if you want, from a modern point of view, approach to the conjecture, and then ask two questions that are motivated by his approach. So first, I'll remind you of what the Birch and Swinnerton Dyer Conjecture is about, and I'll sketch the very general steps that go into proving it in the case of analytic rank 0 and 1. And then talk about what I think Kolyvagin had in mind as far as going further. So we'll always focus on a single elliptic curve defined over Q. And then there are two conjectures that really play a big role in motivating Kolyvagin's work. One is the BSD conjecture, which says that the rank of the Mordell-Weil group of E is equal to the order of vanishing at s equal to 1 of the L function LES. And henceforth for this talk, I will call this R sub alg for the algebraic rank, and I will call the order of vanishing R sub an for the analytic rank. Another conjecture, which Kolyvagin also proved for elliptic curves with analytic rank less than or equal to 1, is the Shafarevich-Tate conjecture, which is the assertion that the Shafarevich-Tate group of E over Q is finite. So these are both theorems when the analytic rank is less than or equal to 1, mainly due to Kolyvagin. But other names that play a massive role are Gross-Zagier, Bump, etc. And the situation more generally is that if Rn is greater than or equal to 2, we don't in a single instance know this conjecture. This conjecture for particular examples is known for particular examples only when Rn is 2 and 3. So if you take a specific curve with analytic rank 2 or 3, and you really want to try to prove that this conjecture is true for that curve, chances are you'll succeed. This is not known in a single case when the analytic rank is greater than or equal to 4. So here's the general structure, which, motivated by Berry's pentagon, I will also describe using a pentagon. There are 5 steps. The first step is to prove that E is modular. The work that at least Kolyvagin did towards this conjecture always made the assumption that the elliptic curve is modular, and fortunately now we know that for all elliptic curves defined over Q. This is Wiles, Taylor, Conrad, etc. Step 2 in Kolyvagin's approach is to find or choose a quadratic imaginary field K such that the discriminant of K is coprime to 2n. The discriminant is congruent to a perfect square modulo 4n. And the twist of E by K has minimal analytic rank with opposite parity to the analytic rank of E. In fact, because this conjecture is known for analytic rank 0, I'm going to assume everywhere in the rest of my talk that E has analytic rank greater than or equal to 1. And the things I'll write down don't quite work in the case of analytic rank 0. So the quadratic twist of E should have rank 0 if Rn is odd, and 1 if Rn is even. So you find such a field. This has been done for every elliptic curve over Q by Bump, Friedberg, Hosstein, Murdy, or Walsh-Bourget. That sort of work. Yes, this is the analytic rank. Let me be explicit about that. Okay?
What is big N?
N is the conductor of the elliptic curve. So modular meaning, thank you for asking, x naught of n maps surjectively to E, and this is the smallest n with that property. Any other questions? So the only thing that isn't maybe completely obvious if you're very familiar with this stuff already is that you want to choose this k, but there's really no other reasonable thing to choose. So this is also, so first is done, 2 is done in complete generality by many people. I'll just put some names here. Murdy, etc. Okay, step 3 is define a subgroup V contained in E of Q. It's associated to K, though. Just define a subgroup like this. So in the case of analytic rank 1, this is the subgroup generated by the Heegner point, Y sub K. In general, Kolyvagin does give a description of a group like this, and that's what I'll describe in a minute. So step 3 is to define a subgroup. And I'll say that this was done by Kolyvagin. Or Heegner maybe, but really it's Kolyvagin in general. Step 4 is to prove a theorem. So prove that if the rank of V is equal to the analytic rank of our elliptic curve, then the two conjectures are true. So BSD and ST are true. So that's the fourth step. And again, to focus ideas on analytic rank 1, this is the statement that the Heegner point has infinite order implies the Birch and Swinnerton Dyer conjecture for the rank 1 curve and finiteness of the Shafarevich-Tate group. However, in this mathematician Allen paper from 1981, Victor Kolyvagin, he makes a sequence of conjectures, which he calls conjectures A, B, C, and D, and proves a theorem like this given a more generally defined V. So this, in fact, is done, again, by work of Kolyvagin. But of course, notice it's conditional on the rank of a certain group, which I haven't defined yet, being equal to the analytic rank, a statement that is not known in any case when the analytic rank is greater than or equal to 2.
How come you say underlying? You proved the implication that you...
Yes. This implication is in here and another paper. And it's there. Okay, now step 5, you can kind of fill in what that might be. It's the underlying thing. So prove that the analytic rank is equal to the rank, oops, in the same order, that the rank of V is equal to Rn. And this is true when Rn is equal to 1. And completely opened in all other cases.
So after the fact, these are basically E of Q.
Yeah, up to finite index, it will be E of Q. And the index will have to do with the product of the Tamagawa numbers, the order of Shaw, and the order of Shaw.
Is there any reason why you put them in that order? Like why not? Why you kind of put 5 after 4?
You could swap the order. Yeah, it's there's no good reason to put it in this order. Except to say, I mean, conceptually, it's nice to say that 1 through 4 are done and 5 remains, instead of saying 1 through 5 except 4 are done and 4 remains. So good to put, I mean, presumably if the strategy of Kolyvagin actually works, then this will be the last step, which will be proved, because the other ones have been proved. So,
Why is there an arrow from 5 to 1?
oh, done. Okay, so here we're done.
1 and 5 are qualitatively different, by the way, because they're relations between analytic and algebraic objects. 2 is completely analytic, and 3 and 4 are completely algebraic.
Okay. So I'm going to momentarily hide this because of this funny blackboard. And then on the top blackboard, I'm going to define V, which will be this basically an exercise in the standard Kolyvagin machinery, which probably a third of the people in this room know well, and the other 2/3 might not. And then I will slide that board up and then continue talking here about just some questions really that arise. Okay? So that's the plan. So don't freak out that I'm closing this. Okay, so section 2, Kolyvagin's definition of V. So the very quick definition for the experts is you take all the Kolyvagin cohomology classes in H1 in various torsion, you take the inverse image in the Mordell-Weil groups, and then intersect them all. Intersect all those groups. But now I give something more precise for people for which that doesn't make any sense. And this will take a couple of minutes. So we have our fixed quadratic imaginary field K that satisfies the hypotheses that I covered. And O sub K is the ring of integers of that quadratic imaginary field. And inside of there, by hypothesis, there exists an ideal I such that OK mod I is cyclic of order n, whereas usual n is the conductor of the elliptic curve. For each L in the natural numbers, let O sub L, which is Z plus L OK, be the order of conductor L inside of O sub K. And let's assume now that the GCD of L and the discriminant of K is equal to 1. Actually, sorry, I want L to be lambda, since I want to allow products of primes and not just one. And I also would like the lambda to be coprime to n. Okay, so when you have this, then consider the elliptic curve C mod O lambda, and then it emits a rational over some field isogeny of degree n to the elliptic curve C mod I inverse intersect O lambda. And the class of this isogeny defines a point in x0 of n, and by the theory of CM elliptic curves, that's defined over the Hilbert class field, which I'll denote by k sub 1. More generally, I'll let k sub lambda be the ring class field of conductor lambda associated to k. What?
The point you've defined is over k sub lambda. I mean, it's
Oh, yes, I'm sorry. Yes. I'm just being stupid. K sub lambda, where k sub lambda is the ring class field of conductor lambda. And I'll call this point Z sub lambda. And now its image via the modular parametrization on the elliptic curve is Y sub lambda, which is pi Z lambda, which is a point on the elliptic curve over the class field K sub lambda. And now I'm going to define a point P sub lambda, also in E of K lambda, which is j lambda, I lambda, y sub lambda, where j lambda and I lambda are certain elements in the group ring of k lambda, of the Galois group of k lambda over k. So j lambda and I lambda are in Z, G, k lambda over k. And their definition is as follows. So the Galois group of k lambda over k is the product, actually over k1, is the product of Galois groups of k lambda over k sub p. No, I don't want to break it up that way. Kp over k1 as p runs through the divisors of lambda. So you could decompose the Galois group of k lambda over k1 like that.
Lambda square free?
Yes, yes. Square free now. Thanks. So decompose the Galois group like this. Each of these is cyclic of order p plus 1 with a generator t sub p.
That's just the fact that the lambda inert is there. It could be a cyclic one if you run it.
Okay, yeah. So that's another hypothesis I'm perfectly happy to make. So yeah, sorry. Let's assume that for each p dividing lambda, you have AP congruent to p plus 1 congruent to 0 mod a prime L. So that's not, well, I shouldn't introduce this yet, actually. So I won't introduce that yet, but yeah, so assume lambda's inert in K. So you have that decomposition, and now I lambda is just the product of I sub p's over p dividing lambda, where IP is equal to the sum for j equals 1 to p, j t sub p to the j. And j lambda is just equal to the sum over g in representatives for the Galois group of k lambda over k mod the Galois group of k lambda over k1, and you lift them. So these are all elements of the group ring of the Galois group G, or the Galois group of k lambda over k. And this defines an element p sub lambda. Now I'm going to restrict the lambdas that I actually consider more precisely. So fix A prime L, and let lambda, I'll call it lambda t sub n, be the set of, so big lambda tn is just a set of lowercase lambdas such that lambda is a product p1 through pt of t distinct primes. And for every single one of these primes, you have ord pi of the GCD of API and pi plus 1 greater than or equal to n. So, what's the confusion? So for each I, yeah, I mean Orts of L, sorry. I equals 1 through t. Yeah, that didn't make any sense.
A sub pi?
Yes, it's A sub pi. So another way to think about this is that API is congruent to pi plus 1, which is congruent to 0 mod L to the n. And now, one of the fairly easy things that Kolyvagin observes is that the points p sub lambda for lambda in here are in E of k lambda mod L to the n E of k lambda. But moreover, I mean, that's by definition if you take their class. But better, they're invariant under the Galois group of k lambda over k. So let's just go through this again really quickly. For a bunch of square-free integers lambda, where you fix a parameter t and n, you define a whole bunch of points p sub lambda, and then in fact take their classes in E of k lambda mod L to the n E of k lambda. And these points have some chance to have something to do with our elliptic curve over Q because of this invariance condition. Any questions? The definitions and notation are identical to what's in every paper of Kolyvagin. So here's the, I need to now define a group V, and here's how you do it. So there's a map from E of Q to E of k lambda, which is just take a point and include it in there. And hence you have a map to this mod L to the n times E of k lambda. And of course it maps into the things that are invariant under the Galois group. So let's do the following very surprising thing. Let's just take the inverse image of the group generated by p lambda here, and we'll get a subgroup of E of Q. So I'll do this over here. We could get a very small subgroup, but let's let V sub L to the n be, just take the group generated by all inverse images of the points that Kolyvagin constructs. Should be L to the n. I'll just put it in. So the inverse image of the group generated by this point p sub lambda, where lambda varies over, well, we have to pick a particular t, and here's the t to choose. The analytic rank of our original elliptic curve minus 1. Okay, so in summary, Kolyvagin constructs a whole bunch of points via CM theory plus these projection operators. These projection operators exactly kind of move the point around exactly to get something that's invariant under the Galois group, but only modulo L to the n. I mean, it's certainly not invariant under the Galois group here in general. Unless the rank is 1. Well, even then, only in special cases. So,
What happens if the rank is 1? Exponent is 0, right?
well, yeah, so you take 0, and then the only point you're ever talking about is the Heegner point. That's it. Yeah. Okay? So there it is. There's something. And one observation. Sure, please.
Why do you want to think of it inside EQ instead of inside EQ mod L to the n EQ? Because it contains all the L to the n model.
Yes. Okay, so Matt's remark, which I like to make, is that this V sub L to the n, it sits between L to the n E of Q and E of Q. And that's just trivial because we're taking the inverse image of a subgroup of E of k mod L to the n E of k. So, I mean, certainly every L to the n multiple of something here goes to 0 over here. So it's in the inverse image. I'm not answering your question, but
That's a question of psychology.
yeah. Sure. Well, you'll see what I do next. So another observation is that as you increase n, the groups get, well, there's a sequence of inclusions like this. I mean, because all you're doing as you increase n is you're making this condition a little harder to satisfy. So you're cutting down the collection of lambdas that you consider. So that's all you're doing. So you have less and less of a chance to have anything interesting going on. Plus, you only contain L to the NE of Q. So these are getting potentially smaller and smaller and smaller and smaller. Except, of course, in the case of analytic rank 1, where you're always just getting the same thing, the Heegner point. So we have all of these. Let's just let VL infinity be what you get at the end. So this is by definition the intersection over all L to the N of, or so the intersection over N greater than or equal to 1 of V sub L to the N. So that's V sub L infinity. Yeah. And then even more daring, as Kolyvagin was, I think, let's define V to equal the intersection over all primes L of V sub L infinity. So even if you don't think this is going to be 0, maybe this is 0. So now there's a question. This is the first of the 2 questions in this talk. So I'm going to write down 2 conjectures, one of which is true. So first I'll start with the pessimist's conjecture. Sure.
It's probably the Heegner point would always be in there, that it's sort of vanished somehow by previous theorems if the rank is bigger than 1.
So, wait, say that again?
I think the Heegner point would be null.
Well, in the case of rank greater than 1, your lambda always is divisible by a prime. So sort of has nothing to do with the Heegner point. It's things that maybe map to it under things, but they're not. A priori, it doesn't have much to do with the Heegner point. So the pessimistic conjecture to make is that V has rank 0 whenever the analytic rank of your curve is bigger than 1. Whenever the rank is bigger than 1. This might be true. Another conjecture to make, the optimist's conjecture, is that the rank of V equals the analytic rank of the curve. For any given curve, one of these is true. Well, actually, it's possible that something in between is true. But what are the odds of that? I mean, come on. It's either going to be this or that. So maybe my question, I'll make my question, which one is true? Are either of them true? Which is true? Or I guess I could say which is true, or is there a conjecture that's more of a person that recognizes shades of gray rather than a pure pessimist or a pure optimist? So which is true, or neither? But I'll tell you what I think. I think one or the other is true. But I don't think that neither is true. So there's a definition. Any questions about it?
Do you think for each curve one of those is true, or you
Yeah.
think one of them is true for all curves?
One of them is true for all curves. Yeah. I'm not telling. But I think Kolyvagin is an optimist, if you look at his paper. Since his conjecture D at the end of the paper is almost exactly the optimist conjecture. So Kolyvagin did think, I think. He didn't exactly say this, but it's almost the same thing.
Could you say something the way you're going to do this about the effectivity or non-effectivity of trying to compute these things for a given?
Sure, I'll say something. It's very difficult, but the question is to say anything at all about whether these V's or V sub L's or V sub L to the N's are computable. So assuming that you've, assuming that you've computed the Mordell-Weil group of E, I think you can compute V sub L to the N for any N. Assuming, yeah, I think you can. I don't think there's any program implemented that does it, but I think that is computable. I got a grad student, Dimitar Jutchev, right there. He, in fact, computed, well, let me write something. He looked at, with Kristen Lauder, the elliptic curve 389, A, and they looked at V sub 3. So remember, this is what you get when you take the stuff Kolyvagin constructs for lambda equals, well, actually, it turns out 5 in this case, but L equals 3. L equals 3. So you get all these points from Kolyvagin when L equals 3. So what he did was he looked specifically at the point P sub 5. So in other words, the point P sub lambda comma 1 with lambda equal 5. And it turns out that that point does give you a subgroup that's not just contained in 3e of q. So in other words, V3.
What is the lambda comma 1? Yeah, you've never had that.
Oops, I'm sorry. Yes, just. So V3 properly contains 3e of q. So they're not equal. It could be that V3 mod 3e of q, so this has rank 2. It could be that e of q mod 3e of q, this is z mod 3 squared. And this V3, well, it has an image inside of here, and it has rank at least 1 inside of here. Maybe it has rank 2. We don't know yet, because the next lambda after 5 is so big that the calculations get really difficult. I don't remember. Do you remember? I don't know. The number of fields are huge suddenly. What's the next lambda after 5 that you have to use for L equals 3? That was the question. Yeah, it's something like 89. Yeah. Moreover, I want to emphasize that in this paper that Dimitar, Kristen, and I wrote, we give an algorithm to compute this piece of lambda, and in addition, figure out what's going on with the definition, but we don't actually fully implement it. So when I say that we've computed this and verified this, I mean that modulo the possibility of, part of the calculation involves floating point numbers, and we haven't provably bound the precision of the floating point numbers that we're computing. That said, it's ludicrous that it wouldn't be right, because at a certain point you get a number field, and if you messed up with your floating point numbers at all, the discriminant would be completely off. But the discriminant is exactly what class field theory predicts. So there's no way it's wrong, but it's not a theorem that this is really not equal to that.
Would it be easy to take the curve at CM in rank 2? So we can
I don't know.
the point individual points might be a lot easier in terms of the field.
But the problem is
Maybe.
finding things in this lambda because it's
Yeah.
very small numerical density of those primes.
Yeah. Yeah, Chebatarov tells you that the set lambda is infinite for whatever parameters you have, but it's kind of small. So I think the best approach actually to this problem in the long run will involve using Ribot's level raising theorem, which is the hypotheses of that theorem are satisfied here. So you can throw a lambda into the level, find something that's congruent mod a prime to the modular form attached to E, and use the Mordell-Weil group of that to, I think, construct this point and sort of get more information. It doesn't work very well for this particular curve, but if you look at the curve 571b, it's another example, 571b, and L equals 3 and lambda equals 11, then you find a congruence with an F, so this is E, which has rank 2, or n equals 2. There's a congruent elliptic curve F of level 571 times lambda times 11. It has analytic rank 1. And I have very strong reason to believe that the Mordell-Weil group of this, F, maps via the appropriate diagram, which I guess I'll write down right here, to give the thing corresponding to P lambda. And this is closely related to what I remember you talking about a few years ago. So, yeah. Yeah, and the diagram, you're not falling asleep like you wanted to. Oh, okay. I'm sure the next part will put you to sleep. Right, E of q mod 3 to H1 q E3. The E and F have the same mod 3 Gauss representation. That's how I chose them. So you have an isomorphism here. And H1Q F3, and then F of Q mod 3. This has rank 1, so it gives rise to a line inside of here. That gives a line inside of here. And what I did was I just did a funny thing. I computed for the line that you get for each point in here, every single prime, so that when you, well, not every, I mean the first like 20 primes, so that when you reduce to the Galois cohomology over a finite field, you get something non-zero. Then I did the same thing over here, and they match up exactly for one of the points here. And it's also the same point that I think comes from one of these. In any case, there's a lot of calculations and like data that is possibly computable related to these v's. And the point of defining them is mainly to motivate further work on them. So I'm not trying to be precise about the calculations here. This is just meant to throw a bunch of stuff up on the board and then say that there are things one can compute. Is that good enough? Okay. All right, so now how are we sitting? So here's this strategy. And all I've done really is explained 3 in a little more detail, namely the definition that Kolyvagin gives of a subgroup. And for all we know, the subgroup could still be 0, even in this example. Because notice that you intersect over all powers of L. And all I did was verify, or we verified that V3 is not sort of as small as possible. But it could be that, when you compute V9, then it's just 9e of q. Who knows? So it could be that this V is still 0. So I am way too lazy to try to approach even thinking about computing V itself on a computer. So I'd much rather think about more theoretical approaches to understanding it. So I'll talk a little bit about maybe kind of just another question about how you might generalize the Gross-Zagier theorem to possibly say something about V. I don't know. Yes?
Another question.
Sure.
In the optimistic conjecture, if you did hit the analytic rank, is the suspicion of Kolyvagin that the index is the essential?
Yeah, he proves that. Yeah, that's his. He essentially proves that, but not quite. He does prove this theorem, though. I mean, if you do hit the analytic rank, you get the BSD conjecture. So that's pretty cool because that says that you've got the whole Mordell-Weil group. So this V is a better thing if this is actually true, you want to be focusing on the V instead of something else, because the V at least you have some hope of understanding. Okay, so I'm going to cover this up again, and now I'm going to make some remarks related to the Gross-Zagier theorem. And that will conclude my talk. So really, I guess this is a naive question. So I'll state a precise question, but probably it will be the slightly wrong question to ask. And my hope is one of the experts in the audience will be able to formulate a better question. And that will end my talk. So here's the naive question. First, let me review very quickly what is proved in the Gross-Zagier paper. So let me this. So kind of the main output of it for the purposes of our strategy is that when Rn equals 1, that implies rank V equals Rn. And the way that's proved, though, is pretty neat. What you do is you write down the point x1 minus infinity in the Jacobian of x naught of n. It's defined over the ring class field, well, just the class field, actually, the Hilbert class field. And then you write down a formal Q expansion, sum n equals 1 to infinity, where you take the height pairing of C and Tn C sigma, Q to the n. Let me decorate this a little more. This is F sub A. Here sigma and A is an ideal class, and sigma is an element of the Galois group of K1 over K that corresponds to A. So that's what's in the notation there. So sigma is in the Galois group of K1 over K, which is isomorphic to the class group, and A is in the class group of O sub K. And these are isomorphic via the Artin map. So for each A in the ideal class group, you write down a formal Q expansion. And the theorem that, one of the theorems that Gross and Zagier prove is that F sub A is a Cuss form of weight 2 for gamma 0 of n. And moreover, amazingly, and if you consider the Peterson inner product, which pairs, oh shoot, well, I guess this will be fine, f sub a with any new form g, you get the square root of the absolute value of the discriminant of k divided by 8 pi squared times the derivative of the special value of L prime a g comma 1, where here L prime a g comma 1, this is a, it's not quite the L function of g, but it's closely related via Rankin-Selberg convolution. So it's an L function, which you can, of course, write down explicitly, and it involves the Fourier coefficients of the modular form g and the representation numbers of the ideal class A. So that's the sort of data that goes into the definition here. Okay, so now the last question that I want to ask, which is very natural given the sort of motivation for this talk, is what might be a reasonable analog, given the definition of V, of this sort of statement? And I will write down one, or I'll write down something. Whether or not it's reasonable, I will leave to you to decide.
In this construction of theorem, there's no elliptic curve, right?
That's right. It's for each new form G. And one other thing, just going back to the strategy, which I want to say before I forget, everything in this strategy, all of the steps 1 through 4 and 5, makes sense with E replaced by an abelian variety defined over Q, whose endomorphism algebra is a totally real number field of degree equal to the dimension of the abelian variety. And moreover, in principle at least, steps 1 to 4 are completely done for such abelian varieties. Not written down really, this isn't really written down for abelian varieties. Yes, Mock. I couldn't hear you, and I really can't. Yes, it's a new form. G and S2 gamma 0 of n, new form. Okay, so now let's define an analog of V, but something that sits inside of J0 of n k1. And I will call it C sub t. We're going to have one of them for each non-negative integer t, and it will generalize this definition, and it will be a subgroup of J0 of n k1. So we're just going to mimic the definition of V, which I just erased. So here's what you do. So you have, remember before we wrote down Z lambda, which is in x0 of n k lambda, and we wrote down that by writing down an explicit, pair of CM elliptic curves. Well, let's just, like was done over here, take Z lambda minus infinity, and we need to push it down to be in K1, so we'll apply I sub lambda, that element of the Galois group, with, and that will give us an element of, well, it still gives us an element of J0 of n k lambda, but it'll have this property. Actually, K1 now. Because notice I didn't apply J sub lambda, so it only gets it down. What?
Oh, you're not going to do J.
Yeah. Just an analogy with this. You don't trace the Heegner point all the way down either here. Okay. Otherwise, you just get the wrong thing. So we have I lambda times this. And now, everything's the same as before. You have phi sub lambda comma n from J0 of n.
1 second.
Yes. T is any non-negative integer. And I'll specialize it in a minute, but fix any t greater than or equal to 0. Yes. Here, lambda is in capital lambda t sub n. So hence the lambda to the n over here. Now, phi lambda n is just the map from J0 of n k1 to this thing right here. And define C sub L to the n to be the inverse image, the group actually generated by phi lambda an inverse of z, I'll call this q sub lambda, of z q lambda, as lambda varies over capital lambda to the t sub n. Okay, so again, it's really the same sort of definition. You just take all the points that Kolyvagin constructs, apply his projection object or projecture to them, and then take the inverse image in here. A priori, you could get 0. Yes?
The condition on p dividing lambda is the p sub p now is kind of like the 0 mod alpha now? What is the condition on p dividing lambda?
Yeah, that's the condition. So you have to use a heck off. Yeah. Yep. So there's a condition on lambda. Yeah. Now let c sub L infinity equal the intersection over all n of c sub L to the n, and c equal the intersection over all L of c sub L to the infinity. Ct, sorry. Forgot my t. So now I've defined a subgroup of J0 of n K1. And now if you just fix a basis for this subgroup mod torsion, you can formally write down something exactly like this and ask a question about it. So fix a basis. Yes, exactly. So fix a basis C1 through C, well, we don't know yet, M for CT, and consider the formal sum f sub a t equals the sum, as n goes from 1 to infinity, of the determinant of the height pairing matrix, where you pair ci with tn cj hit by sigma times q to the n. And there you have something that generalizes this construction, but for all t. And then the question, or questions really, one is f sub a t in S2 gamma 0 of n. And of course, the pessimist would instantly say, sure, because this c that you've constructed is surely 0 in any case when it's not something for which the Gross-Alge theorem is already known. But the optimist might still want to prove this, or at least try to understand whether it's true or not. And then question 2 is very natural. If you Peterson pair f sub a t with g, does that have any relation at all? So this is the Peterson inner product. Does that have any relation at all to L a tth derivative g comma 1? Or I'll put this in quotes because maybe this isn't even the right thing to consider.
You want P to have
G should be a
You're not worried about the P to have a 0?
You're not worried about that one's p that vanished to order less than
yeah, so am I.
We want P to have vanish. The alpha P actually vanish in order. Here's a very nice question.
I'm happy to make, it's a question, so I'm happy to ask that easier question, since it's a question about less G's. Yes?
Suppose CT is the 0 group and the basis is empty. And then
Yes.
you determine the 0 by 0.
I mean that to be 0. Yeah.
So that would be
Well, in that case, define it to be 0. Yeah.
when it's more than 1 by 1. I mean, the way we prove the modular form way 2 is because the sum of Pn q to the n. Pn at any point times q to the n, the modular form of way 2 is basically formal reason.
Right.
Start taking a determinant.
Sorry.
Okay.
So it's a question, and it looks weird, but it's still a question. I mean, it's not a question sort of set up to be easily answerable using any known techniques. Otherwise, it would have been already answered, presumably. But those are my two questions. I'm not saying at all what I think, but the two questions are, one, is the group V that Kolyvagin considers in that old paper, is the pessimist right? Is it just 0 when the analytic rank is greater than 1? Or is it actually large? Does it have rank equal to the analytic rank? The second question is, if you formally write down a power series that involves this group C that I've defined, does it have anything to do with modular forms? And if so, does that modular form have anything to do with L functions? Okay? So hopefully those are meaningful questions. I don't know what the answers are at all. Thank you.